In this FRQ for question number A, it asked us to derive an expression for the maximum height of the dart during the flight in terms of v, g, and theta. And maximum height depends on vy. So viy is equal to sine of theta times vi. And then we can use the formula, the common form, to find the maximum height. So vfy squared minus viy squared is equal to 2g delta h. And since it starts at 0, it's basically h, so it's the same thing. And vfy it doesn't exist at max height, that's why it's a max. And then we can plug in viy for negative sine theta vi, and then we can square both of them over g, and then I'm sorry. G cancels out the negative, so it becomes sine square theta is times vi squared over g is equal to h max. And now on to question number B. It says, determine the kinetic energy of the dart just before it strikes the block. And we know that since there's no VIY at H max, which is when it hits it, then there's only Vx. So the formula for kinetic energy, Ke, is equal to 1/2. And I'm going to call the dart M1 because it's the first mass represented. And then it will be V squared. And then we know that since v is just equal to vx squared plus 0, so v is equal to vx, and vx is equal to cosine 30 times 10 meters per second is equal to 8.66 meters per second. I'm sorry, I'm kind of sick right now. Okay, and then we just plug in Ke is equal to 1/2 to 0.02 kilograms times 8.66 meters second squared. And that comes out to 0.75 joules. And then for number C, it asks us to calculate the horizontal distance. Sorry. Can you give me like 5 seconds? Okay. C asks us to calculate the horizontal distance between the launching point of the dart and the point of the floor directly before the block. And how we do that is that we know that it stops at Vmax. So then VFY is equal to VIY plus GT. And then to solve for the time, we just do VIY equals GT. And then we already solve for, we can solve for VIY by doing the same thing that we did for VIX. VIY is equal to 10 meters per second times sine 30. And then we plug it in. So it'll be equals to 5 meters per second. And then 5 meters per second divided by 9.8 meters per second squared is equal to T, and that is 0.51 seconds. And now all we need to do is we just plug it into the formula. Delta x is equal to Vix t plus 1/2 at squared. There is a is equal to 0 because there's no acceleration in the x direction. And now we just solve for it, and then x is equal to 4.418 meters. Okay, and then D is calculate the angle in which the dart and the block on the string will rise before coming momentarily to rest. So how we can do that is D, we can first start off with the linear momentum, conservation linear momentum. So M1 and then V times Vx is equal, I mean V1 because like, I'm sorry, yeah, V1, which is basically Vx, is equal to, since it's an inelastic collision, M2 is M2 is the mass of the block, and because it's the only other mass in the problem. So then, and then Vf, this is Vi. And now we just plug everything in. M1 is 0.02 kilograms times, and same thing as before, it's 8.66 meters per second, 8.66 meters per second, and then M1 is 0.02 kilograms plus 0.09 kilograms times Vf, and then we can solve for Vf. Vf is equal to 1.574 meters per second. And then now we can do MEI is equal to MEF, and because of conservation energy, and then that's just KEI turns into potential energy, PEF, and 1/2 M total. So M total is just M equals M of T, and so it's easier for me to write. And then VI squared, VI is just VF in this situation, because that's when they started colliding, and then it'll be total times G times H, and then the m's cancel out, and then H is equal to, wait, let me just put VI is equal to VF. H is equal to 0.126 meters, the change in height, and then to get the actual height of the length of the pendulum, we can do H is equal to 2 meters minus 0.126 meters, because 2 meters is the length of the pendulum, and that is equal to 1.873 meters. And then we can solve the angle of this maximum height by doing cosine theta is 1.873 meters over 2 meters. And then we can do inverse cosine. Inverse 1.873 meters over 2 meters. And then the meters cancels out. And then theta is equal to 20.487 degrees. And then for number for number E, to calculate E loss, we can do the same thing. Well, we can set it up with energy. So we know initially there's KEI, and then at the end we're trying to find how much E was lost. So we can do kinetic energy that was kinetic energy and E lost. So we know KEI is 1/2, before the collision was 1/2 m1 VI squared equals 1/2 m total, which is nt, VF squared minus E lost. And we already solved for all these variables, so we can just plug them in. And then, wait, let me just mark this off. Okay. And then 1/2 0.02 kilograms times 8.66 meters per second squared, the 8.66 is equal to 1/2 0.02 kilograms plus 0.09 kilograms, 1.57 meters per second squared minus E lost. And E lost is equal to negative 0.613 joules after you solve it all out. For number F, we're trying to find the block is a simple pendulum, and calculate the time between when the dart collides with the block and when the block returns to original position. So we know when a simple pendulum completes one whole period, it comes from the original spot to each of the amplitudes back to the original spot. But in this case, when it goes from its original spot to one of its amplitude in the right direction, it comes back to the original spot, which means it completes only half of the cycle. So that means the time period is half of the time is half the time period. So basically, t, the time, is equal to t over 2, and we can represent that with like a little graph, of the XM chart, and t the xt graph, I mean, t is in seconds, and then it goes like this, and this is we know because one period is this whole thing, but since it starts at 0, it only comes to the amplitude and back to 0. So that's only t over 2. This is only t over 2. So now that we know it's t over 2, we can find the time, the period, and then we divide it by 2. So t is equal to 2 pi L over G. It's L over G because that's the formula for a simple pendulum, and you just replace the constants such as m. You can just replace the variable, which is m and L, on top. You can replace them together, and then the constants, which is G and K, you can just replace them with each other, and yeah, 2 pi over 2m divided by 9.8 mm squared, and then t is equal to 2.834 seconds, and then t is equal to 1.419 says. Yeah, and that's the time that it takes for the block to return to its original position. And let me just flip the page. So sorry. I don't have enough space. Okay. And then the next one is the block. Okay, G. We have to sketch the graph. Let me first sketch out the graphs. So the XM chart, the XM graph, XM TS, and then V, which is represented in meters per second, to time, which is represented in seconds. And we have acceleration, which is represented in meters per second squared, AM/s squared. Let me switch my pen real quick. Sorry, this one's running out of ink. Okay. And then it's in the variable seconds. Okay, first of all, we know that since it loses energy, the max energy Vmax occurs when the position is at 0. So we know Vmax is just the V that we found at the beginning, which is 1.57, after we found the velocity after it collided. So that's the Vmax. That's the max velocity that will be Vmax. And for Vmax is equal to AW, and then 1.57 meters per second is equal to A. And then we just need to find omega, and omega is W radical G over L, and that is equal to 2.21 rad/seconds, and we can put that in 2.21 rad/seconds, and then we divide it 1.57 s divided by 2.21 rad/second is equal to 0.7 meters is equal to amplitude. And now for A, how we can solve for the A max is that we can do omega squared times amplitude is equal to A max. And then W squared is, we already have W, and then 2.21 rad/s squared, the whole thing, times 0.7 is equal to 3.43 meters per second squared is equal to A max. And then now we just need to graph it and represent the label all the points. And then since we know what the amplitude is, we can that's our maximum. So oh yeah, we can also solve for our time. T is equal to, wait, we already have our time actually. We already solved it in the prior problem. And then now we know that the amplitude occurs at 0.25 times t, which is 1/4 of t. So that's 0.715 seconds in the x-axis, and then in 0.7 meters in the y direction. In the y-axis, which represents the meters, and that represents the amplitude. And we can do the same thing at the intersection. The intersection, sorry, one is 1.42 seconds, and the x direction is 0 meters, and then the same at here, 2.12 seconds, and it'll be the same amplitude but in the negative direction, so negative 0.7 meters. And then right here, the same thing, 2.83 seconds, and then 0 meters. And then right here, this is just 0 seconds and 0 meters. And now to graph our V graph. The V graph is the derivative of the sine graph, so it'll be a cosine graph. So you do this so it looks nice. Okay, that's my cosine graph, and it starts off at the maximum, which is 0 seconds, but at since the position here is 0, then at the start at 0 is when Vmax occurs. So then that's when Vmax is, and that's why it's a cosine graph. And that is Vmax is 1.57 meters second. And this is right here is the same as the other graph, but 0.15 seconds, but 0 meters per second. And right here it's another Vmax, but it occurs at 0 right here, which is 1.42, because Vmax always occurs at position 0, 2 seconds, 1.57 meters per second. And then this V min happens at the X max, because there's no speed at X max when it can't go any further. So it'll be 2.12 seconds, 0, and then right here is 2.83 seconds, and then it'll be Vmax again, 1.57 meters per second. And then right here I forgot to put the negative since it is in the negative direction. And then for the A the A graph, the A in simple harmonic motion, it always points to the opposite of X, because as it's the opposing force. So as it goes into the X direction, the A, or the force in the acceleration, wants to go to the opposite direction, back to the middle. So when it goes to the amplitude in the negative direction, then acceleration would be in the positive direction to equalize it. So then A is equal to A max, and then we can label the max and mins. This is probably boring, but yeah, we already found the A max, and A max is 3.43, and it happens at the same intervals of the amplitude, so it will be at 0.71 seconds, and it will be 3.43 m/s squared, and then right here at 0 it will be 0, 0, and right here it will be 1.42 seconds, and then it will be 0, and right here it will be 2.12 seconds, and it will be, and this acceleration is in the negative, I forgot to put that, and then it will be 3.43 meters second squared, and then right here it will be 2.83 seconds and 0 meters. Whew. Okay, now it's just H and I, and H, let me use this one. Oops. And H basically asks us to determine the magnitude of the tension in the spring when it reaches the angular position of theta max divided by 2. And since we already found theta max, we can use that to solve for it. So then first let's set up the first equation of what's happening at theta divided by 2, theta max divided by 2. F of c equals mv squared over r, and it will be m total, so mtv squared over r. Let me rewrite that. Fc equals mtv squared over r. Mt is m total as mentioned, and then we can just set it up. T minus fgy is equal to m total v squared over r, and then t minus, to solve for fgy, it will just be mg, sorry, I'm just checking, cosine theta divided by 2 is equal to mtv squared over r, and t is equal to mtv squared over r plus mg cosine theta over 2. Okay, now that we have everything we need to solve, we already have mg and we have cosine theta over 2, but however we need to know what v is. So v is the variable that we're trying to find, but however let's find theta over 2 first. Theta is over 2 is equal to 10.24 degrees with the data that we used before. And now we can solve for the delta H, how much it went up because of how much it went up at 10.24 degrees. So we can do that by cosine 10.24 is equal to times 2 meters is equal to 1.96 meters. And we know that delta H is equal to 2 minus 1.96 meters is equal to 0.43 meters. And then now that we have the height, we can do MEI equals MEF, the conservation of energy. And then we know that 1/2 mTVI squared is equal to 1 mTGH plus 1/2 mTVF squared. And you can cancel out all the mass total, and then it will just be 1/2 1.57 meters per second squared, 1.5 meters per second squared, minus 9.8 meters second squared times 0. Oh, oops, this is 0.03, and this is 0.03 meters is equal to 1/2 VF squared, and VF squared, VF is just equal to 1.37 meters per second. Now that we have VF, which is V at the point of theta max theta, T is equal to 0.11 kilograms times 1.37 meters per second, then square that, and then it's over 2 meters, plus 0.11 kilograms times cosine 10.24 times times 9.8 meters per second squared, and then T is equal to 1.165 newtons. Whew, almost done. 1.65 newtons. Okay. Now that we have one question left. Okay. For question number I, for the first question, it asks us if a dart with more mass is launched at the same speed at an angle. The dart collides with the stick and sticks to the same wooden block. Would the data max that the dart and the block's weight increase, decrease, or stay the same? The data max would increase because data max would increase because linear momentum is conserved. Wait, let me explain it first before I write it, because writing takes a lot of time. So basically, since linear momentum is conserved, you still have to do the same thing to find final velocity. So, and velocity in the beginning is the same, so that means linear momentum in the beginning is more, the initial momentum is more, and in return, VF is higher, and mass cancels out, and mgh equals 1/2 mv squared. So kinetic energy relies on the same velocity, but since v is higher, then the height will be higher. So basically, data becomes higher since it goes up higher. The height becomes higher. And let me just write that down. Because linear momentum is conserved, it has a high initial linear momentum due to a bigger mass, and in return, a higher VF after collision, and mass cancels out, and mgh equals 1/2 mv squared. M total cancels out, but it's just m. So h is greater than h1 regularly, and theta becomes bigger. Theta 1 is equal bigger. I mean, theta is bigger than theta 1. Okay, now for the last question, I'm trying to do it really quick so I don't waste more of your time. Okay, the period of oscillation after collision increase, decrease, or stay the same. It would stay the same because mass has no effect on the period of the simple pendulum, as it depends on the length of the string, because t equals 2 pi over radical lg. I mean 2 pi times radical lg. It would stay the same because period depends on length of string, not mass. 2 pi radical lg equals t. And then that's it. Thank you for listening.